square. Radius vector means from the axis of rotation. If something is rotating, there must be an axis of rotation with reference to which it is rotating. So that axis of rotation separation to the point of calculation is actually known as the radius vector, basically the r that we put. So moment of inertia is basically the rotation of the mass, means the rotational analog of mass is moment of inertia. Whatever function the mass does in linear motion, the same function is done by moment of inertia. How much moment of inertia does an object have when it moves? Like this we say. So meters, you have kg meter square as the unit, and CGS unit will be gram centimeter square. This is one thing which we did, and one numerical also we did, this lengthy numerical we did, based on mass per unit length, ml square by 12 came. So do one thing, write down this much part first, both of you. Then I'll start with different object moment of inertia. We'll share take the video lecture from the last class for the numerical that will be left. But please write down this book. Okay. Aisha, they are just copying the portion of the last class. You were there already in the last class. So ml square by 12 was the last portion that we did. Just check, Aisha, what have you written? Did you could you copy the question or not? Just tell me one thing. That's what I wanted to know. Could you copy the last question properly or not? Aisha, just check because you were there in the last class.
Yeah, ma'am. We had to start with a circular ring. I is equal to ml square by
Okay,
I
ml
square.
square by 12, that part you have written?
Yeah, ml square by 12.
Neha, have you written?
Yes, ma'am.
Okay. Okay, so I is equal to M R square. Now for this question specifically, just I'll tell you at the last if the time is there, or you can see the recording. Just remember, whenever a rod is there and across its center, so moment of inertia of few things you already have to remember. Okay, the axis is present. So L by 2 is the length. So the moment of inertia across this rod will be ml square by 12. So for a few things, I'll tell you the moment of inertia, which you need to remember it from your end and come revise. Okay, it's a time. Aisha, go and pray till the time I'll brief them about moment of inertia. Nabila, do you also have to leave right now for
Okay.
namaz?
No, ma'am.
No, not right now. Okay. See, So then Neha and Nabila, we can discuss this and we'll start the discussion further. See, like a moment of inertia, you will be asked to calculate about a specific axis. If I say this is a circular disc, now there's a perpendicular axis present like this, or the axis of rotation is like this. Something if it is rotating like this, so this becomes the axis of rotation. If something is rotating like this becomes the axis of rotation. Are you getting it? Axis of rotation. If let's say, see, this is present. If I have this as my axis of rotation, so this will be rotating like this. But if I have this as my axis of rotation in the middle, so the object will be rotating like this if this axis is in the center. So do you get how significant the axis is? You should know where the axis is located. And from the axis to the periphery, that will give you the radius. Now, if the ring is present, let's say ring has a mass m, radius is r, and this is its axis. So simply mass is m, r is the radius, mr square will be the moment of inertia of a ring. But see, where was the axis? Perpendicular to the plane, passing through its center. Then only you could see, yes, this is R. Otherwise, it would have been different. How you have to solve for different axes, that we'll see later, because few things you have to remember also from your end. But is this much part clear? MR
Yes,
square,
ma'am.
easy. Okay, write down this one. Now, see, let me tell you and discuss this question. This says you have to calculate the moment of inertia about a rod. Now, the axis is at passing through the center. Like if this is the rod, let's say this is the rod. Axis is perpendicular to its length and passing through its center, this axis. If this is the axis of rotation, so how will it rotate? Like this. So what's the moment of inertia in that case? If it is rotating in that manner, what's the moment of inertia? This is what we are asked to do. Now, here, this is more like a derivation. This is actually not like a question. More than a question, it's actually like your derivation. So what we do, we take a very small length. And remember, I have told you before also, whether it's center of mass or its moment of inertia, your axis will act as an origin. Moment of inertia is truly for your rotational motion, while your center of mass was for translation part also. So here the axis is present, and along the axis the rod will rotate. Now this is taken like the origin. So this is L by 2, L by 2, but the edge you will take one as minus L by 2, other as plus L by 2. One edge as minus L by 2, other edge as plus L by 2. Because it's like the coordinates. How do you take the coordinates? If I give you a number line or the axis, whatever value you have, you are going to put negative sign over here. And whatever value you have over here, you're going to put a positive sign. Now, you have any variable value, then you use this formula for the moment of inertia. I is equal to integral of dm x square, integrating from x1 to x2. Basically, you have taken a very small piece from this rod whose length is dx over here and mass is dm. Now we have to find out what's the value of dm, because you cannot integrate it like this. If variable is mass, then put the dimensions of mass. If you are integrating, if you're putting the limits of x, you'll have to write x. So what we do, the rod of length L has the mass m. Mass per unit length will be m by L. So for unit length, you know, 1 meter, you know, for unit length, you know. So for how much length do you require? Dx. So dx length will be m by L into dx. So that is actually dm. Mass of the rod of length dx was dm, which we assume, and dx value we have calculated as m by Lx. So you put it here, m by L dx, x square was already there. You integrate it from minus L by 2 to plus L by 2. Okay. When you put in all the values, you will finally get the answer as ml square by 12. So just write down this part till here. And after this step, if there's any trouble with the calculation, please let me know. But at least you write the question. Have you understood a little bit of the basics in detail, and slowly you can see it from the recording? But this much, have you got it?
Yes.
Neha? Okay. Write down this too. Okay, done, both of you?
Yes, sir.
Okay. See, now let's start with the moment of inertia of few figures, which you need to remember across their different axes. See, when we have a circular ring, this we have already discussed that if the axis is passing like this, then the moment of inertia is mr square. Okay. If the the axis is parallel to the diameter like this, then it is mr square by 2 for a circular ring. I'll write down these things for axis also. Here the axis is
Mom, how do we
parallel.
know where the axis will be?
What?
How do we know where the axis will be?
It will be given in the question or the figure.
Okay.
Parallel to the diameter. The axis, you just need to know the meaning of the axis should be clear. Like if it is parallel to the diameter like this, so body will rotate like this. This is how the body will be rotating. Means rotation will occur across it. If it is like this, so body will be rotating like this, means across this. So I hope you're getting that point. And this one is perpendicular, which we have discussed also as our first question. Perpendicular and passing through center. And passing through the center. So that is, these are the two which you have to remember for a circular ring. Now, as the modifications will come, different axes will be given to you, different points will be given to you. You will see how this will help. First, you should know the basics. Then for a disk is a solid object. Okay, so mr square by 2 is for perpendicular and passing through the center. Perpendicular and passing through the center. I is equal to mr square by 4. This is again parallel to the diameter.
What's the
Parallel.
difference between circular ring and disk?
Okay, Nabila, no problem. Circular ring and ring, ring means which is a ring. Ring means there is no mass present inside like this. This is a ring. There is no mass present inside. Hollow. It's hollow from inside. And disk, which is completely filled like this. This is completely filled. This is a disk which is completely filled. Mass is present here also. That's it. Okay. Like you can take normal rings that we wear and the 3D discs that we have, anything, plates. So those will come under that. So parallel to the diameter. Then for cylinder. Now cylinder also hollow and solid. Hollow cylinder means there is nothing inside. It's hollow. When you cut and open it, you can see air. Solid means it's completely blocked. Means it is made up of material. So hollow cylinder, when the diameter, when the axis is passing through its center and perpendicular to it. For the hollow one, remember it's just like the circular ring. Just remember it like the circular ring. Means mr square by 2. And for a solid, remember it like mr square by 2. This is just mr square for a hollow cylinder. This is mr square by 2. These are when these axes are fixed. If I give you a different case, we'll see how to use. There are two laws that we'll have to apply. Those laws will give us the resultant moment of inertia. We'll discuss all these things. So hollow and cylinder. Sphere. For a hollow sphere, it's different, 2 by 3 mr square. Solid sphere, it's different, 2 by 5 mr square. Hollow means it's empty inside. Solid means complete mass is present within the sphere also. And for the rod, this we have derived also. So all these can be derived too. So when the axis is perpendicular to the plane and passing through the center. Through center. That's the rod. And when the axis is towards the edge of the rod, it is ml square by 3. You can derive this one also. How? Same thing that we did, but here axis is here. So this becomes your origin to L. We earlier in the previous case, we took this, then this had to be minus L by 2 to plus L by 2. Here the limit will be 0 to L. That's why it's directly ml square by 3 will be coming. So this also can be derived and it can be asked in the exam also. So first tell me, have you understood this much? For every figure, you need to remember this with their axis. Write it and try to memorize it also when you're writing. Copy till here, then we will discuss few more things. Is it done? Others have also written. Okay, see now few things, dynamics of rotational motion, understand this before we combine all of the questions of moment of inertia. Specifically, exclusive questions of moment of inertia, I'll tell you, but many questions are there with combination because mass is involved in a lot of things that we have studied earlier. See, when we talk about the force, force becomes torque, mass is the moment of inertia, linear acceleration will become angular acceleration. So what's the formula now? Tau is equal to I alpha. Okay, F is equal to ma there in linear, and here it is tau is equal to I alpha. All these things should be remembered by you. Next is momentum. Momentum is equal to mass into velocity. Momentum is equal to mass into velocity. So linear momentum will be angular momentum. Angular momentum we have done in the last class as well. And I told you this formula too. Now linear mass will become moment of inertia. Linear velocity will become the angular velocity. So L is equal to I omega is also very important. Conservation of angular momentum we will be discussing. Okay. Next is the work done. See, work done is the same in both of these, but force will be torque and linear displacement will be angular displacement. This I think I mentioned also in the last class. This is very important class from examination perspective. Torque is also important. Kinetic energy I'll be discussing today only. So kinetic energy is equal to half I omega squared. So just write the analogs that we have been doing. Whatever we have studied in linear motion. Like, look at this question. This says a flywheel of mass to 25 kg has a radius of 0.2. Means mass is there, 25 kg. Radius is 0.2 meter. What force should be applied tangentially to the rim of the wheel so that it acquires an angular acceleration alpha is equal to 2 radian per second square. Now, it is asking what is the force? Now, rotational force, we are asked to write. What's the force? Means what's the torque applied, right? What's the force applied tangentially? See, torque is equal to I alpha. Alpha is already there, means moment of inertia is missing. This question I have taken and I have not done the detailing of moment of inertia because let's do what we have just studied so that this is fresh enough. And that's why I've added these 4 points also in here. So study in this sequence only for the example. Now moment of inertia is missing. Now what do we have? A flywheel. Flywheel you can understand like a frisbee. So what should be the moment of inertia that we should use? Formula, tell me. Look, the figures that you have drawn, I gave, I think, sufficient time so that you could understand each and every figure. Which of them should we use?
This.
Disc one, exactly, very good. So a flywheel of mass 25 kg, this says. A flywheel is like a frisbee, that's a disc. Now, what force should be applied? Aisha? Aisha, you there?
Yeah, ma'am.
Yes. Aisha, you were asking how do we know about the axis. Now look, if it is not mentioned without any figure or without any direct mentioning of the axis, it has given what force should be applied tangentially to the rim. See, if I have a disc, if this is a disc, tangentially means like this. This is what a tangent to the circle would be. So without even specifying, do we know which case is this? We've already seen this. So what should be the moment of inertia formula? Tell me. Somebody answer.
MR square by 4.
MR square by 4. Perfect. MR square by 4. So I will be equal to mass is 25. Radius is 0.2 whole square divided by 4. This is the moment of inertia. And for torque, it will be I into alpha. 25 into 0.2 into 0.2 into alpha is 2 divided by 4. So this will be 2, this will be 0.1. This is equal to, this 2 into 25 will be 50. That is 0.5. Unit will still be Newton meter. Use the unit as Newton meter only. That's the torque that will be applied. Clear?
Yes, ma'am.
Yes, ma'am.
So this is how you need to identify the axis of rotation. Where will the force be applied? So wherever the force will be applied, if I have this, let's say this is the rod. If I apply a force here, it will move like this. If I apply a force here, it will move like this. So this becomes the axis of rotation, this part. This is the axis of rotation because it is moving like this. So this is how you have to identify. Okay. Write it down. Angular momentum also we have to see. Write it. Okay, can we come to angular momentum conservation? Okay, Neha, you have an exam.
Yes, ma'am.
Okay, so your exams are ongoing or that's the last paper?
Last paper is on 6th October.
Okay, is the physics exam over?
No, it's on Monday.
Okay, it's physics only. Okay, so what are the syllabus is
First
coming?
5 chapters.
First 5 chapters till work energy.
Yes, ma'am.
All right, so that must be prepared. I hope, Neha, you'll do well because that was done in
Yes.
detail. Any problem with that? Any query, any doubt?
No, ma'am. I have to do question papers now. So,
Okay, so once you have gone through that, means the first time that we study, that one is done.
yes, ma'am.
Okay. All right, Neha, then you leave, you study those portions, and please update me tomorrow. Will you come tomorrow?
No, ma'am. I won't be coming.
Okay. All right, then. Fine, Neha. Just before you come, because probably by 6th your paper will be over, no? So 6th means, okay, next week it will touch. If it is 6th, then that is Monday. Next weekend also will be involved. So, fine, Neha. You can leave. Okay.
Thank you, ma'am.
Now, class, talking about the conservation of angular momentum. This formula, angular momentum conservation, class, is basically, see, the way we say na, conservation of linear momentum that we have studied. Conservation of linear momentum means, see, F external is there, okay, and F external is 0. That's what we say. So what did we used to say? F is dp over dt. So this rate of change of momentum is equal to 0. Then we talk about conservation of angular momentum. So torque external is equal to 0 in this case. Just related with this, you'll be able to remember it very easily. And torque is d theta over dl over dt. I've written theta. This is dl over dt. This is dl over dt. So your dl over dt will be 0, means there is no rate of change of angular momentum. So L is constant. There is no change. Now L is equal to I omega. So I1, so basically you can say, see, L is equal to I omega. This will remain constant. Means I1 omega 1 equal to I2 omega 2 equal to I3 omega 3. This will be constant. This will remain. And this is very important. In physics also, means for your applications also, this is a very important part. And for your numericals, definitely it is. Applications, I'll tell you. So this is what you need to know. Now see, remember, when I say I omega is constant, look at its formula. I into omega. See, if we have to make this constant, if we have to make this constant, this shouldn't change. Let's say moment of inertia decreases. Angular momentum will increase in the same ratio so that their product is constant. Okay. Similarly, if moment of inertia increases, angular momentum will decrease so that L remains constant. Main purpose will be L should be constant. So if you have two objects, I1 omega 1 is equal to I2 omega 2. This increases, this decreases. If this increases, this decreases. Like this, each of them will balance each other. That's the main point which you should know. And based on this, you have the application-based theoretical questions also in the exam. Write it. I'll tell you first the application. See, talk about the conservation of angular momentum, a little bit of the applications, and that's a homework for you. You have to go and open your NCRT for this. See, rarely I tell you to go through the NCRT because most of the things we do in the class itself, but this also I'll tell you, but go through the NCRT also once because questions come from this. Like rotation of the earth. If I talk about the rotation of the earth is there, it is rotating. This is the axis of the rotation, okay? It's the axis of rotation. Radius is also there. Okay, moment of inertia will be present. So radius is there, mass of earth is present, so definitely it will have its own moment of inertia. It is rotating with some angular speed omega. Now, if the radius of the earth is increased, if you increase the radius of the earth, okay, what will happen? The moment of inertia will increase, or even if you increase the mass of the earth, moment of inertia will increase. If moment of inertia increases, the angular speed of the earth will decrease. The speed with which it is rotating means day and night, they'll be longer because speed has decreased. Day and night will be longer. Why? Why will it decrease? Because angular momentum cannot change. Angular momentum will be constant because there is no applied external torque present. One more example that is helpful for the numericals is ballet dancers there. So ballet dancers, what do they do? They usually, when they are dancing, they have this rotating frame on which they dance. So they have their radius. If I decrease the radius, what do they do? First, they have their arms spread out. The ballet dancers, they have their arms spread out for dancing. So what happens if this is there? The radius increases. Radius increases, so mr square, that is moment of inertia, will increase. So moment of inertia increases, angular velocity decreases. Now when they have to spin fast to dance, what do? They immediately, whenever they have to, they immediately lower or reduce their or bring their arms closer to their body. Ballet dancers, they have their arms like this, they are spinning with a less velocity. So what do? They immediately, while they are turning, they put their arms closer to their body. So this decreases the radius. What happens is this decreases the radius. Radius decreases, moment of inertia decreases, angular speed increase. So they spin faster. So that's why the ballet dancers do this often. If when they dance, they bring their arms closer. So this decreases the radius. Even if you are spinning, you take your arms spread out, you'll spin slowly. And then while spinning, just bring your arms closer. So what will happen? Moment of inertia decreases, angular velocity increases. All this because I1 omega 1 is equal to I2 omega 2. Am I clear till here?
Yes,
ma'am.
ma'am.
Okay, then write down this. And please go through the NCRT one for this. This is almost the end of the chapter. One class is needed to sum up everything. Practice few questions and practice moment of inertia. Actually, moment of inertia's axis part has been deleted through your syllabus. But anyways, write it. We'll see. One more class is needed for this. That's it.